Welcome to EDU World Space.
Okay, in this problem, in the first part, we're talking about the Hubble telescope. So this is part A. They say that it is at a height from the surface of Earth of 610 kilometers. So that's equal to 610 times 10 to the 3 meters. So kilometers, 10 to the 3 meters. And we also need the mass of the Earth, which is 5.97 times 10 to the 24 kilograms, and then the radius of the Earth, which is 6.37 times 10 to the 6 meters. So to find the period of the Hubble Space Telescope, we can use Kepler's third law, which says that the period squared is equal to 4 pi squared times the semi-major axis cubed over gravitational constant g times the mass of the object that's being orbited, which in this case is the Earth. Now, the semi-major axis is going to be, so if this is the Earth and this is our satellite, semi-major axis means the distance from the center of the object to the object that's orbiting. So this is A, and then that can be broken up into the radius plus h, which is the distance from the surface to the satellite. So we want to find the period. So let's go ahead and just take the square root of both sides and plug in the values. So we have a 4 pi squared times the semi-major axis, which is going to be the radius of Earth plus the height. So that's 6.37 times 10 to the 6 meters plus 610 times 10 to the 3 meters. And this whole thing is added together and then cubed. And that's over the gravitational constant, 6.67 times 10 to the negative 11. That's newtons, meters squared over kilograms squared for the units, times the mass of Earth, 5.97 times 10 to the 24 kilograms. And that is going to give us a period of 5,806 seconds. You can divide this by 60 to get 97 minutes, so about an hour and a half. So then we can move on to part B. And in part B, we are talking about geosynchronous orbits. So in order for us to have a geosynchronous orbit, the satellite or object orbiting has to have a period that is the same as the rotation of Earth. So the rotation of Earth is 24 hours, approximately 24 hours. And we want to get this into units of seconds. So let's just multiply this by 60 minutes per hour, and then 60 seconds per minute. And that way hours cancel out and minutes cancel out. We'll get seconds. And this is about 86,400 seconds. So we can just use the same equation for Kepler's third law, but now we're solving for A, and then we can find the height from the fact that A equals R plus H. So solving for the semi-major axis, we get T squared times the gravitational constant times the mass of Earth divided by 4 pi squared, and all of that to the 1/3 power to get rid of the cubed on the semi-major axis. So plugging in everything, that's 86,400 seconds squared times 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared times 5.97 times 10 to the 24 kilograms divided by 4 pi squared. And then we take that to the 1/3 power, And that is going to give us 4.22 times 10 to the 7 meters. Now, this is the total distance from the center of Earth, so we have to subtract the radius of Earth. The height is going to be a minus r, so that's 4.22 times 10 to the 7 meters minus 6.37 times 10 to the 6 meters, which gives us a height for the satellite of 3.59 times 10 to the 7 meters. So this is the height that it would need to be in order to be parked, or need to be in a geosynchronous orbit. So then in part C, they ask if this can occur at any point over the Earth's surface, and the answer here is no. So when we have something orbiting the Earth, so if it's at the equator, the Earth's axis, and it's orbiting around this axis, then if it's at the equator, then it'll stay parked if it has a period of 24 hours. However, if it's parked at some other point, it's going to drift north and south as the Earth turns. So the answer is no. It must be along the equator.